So in the last piece of 2002 number 5 here, it wants us to show that the rate of change of the volume of water in the container is, due to evaporation, is directly proportional to the exposed surface area of the water. So the rate of change of the volume of water in the container, we looked at this a little bit in part B. We defined that to be dV dt. So the rate of change of volume is dV dt. And what it wants us to show is that this derivative, this rate of change, is directly proportional to something else. Well, in math, if something is something else, it's equal to it. And if something's proportional to something else, that means there's some constant of proportionality that we multiply by to make the equation true. Now, what we're supposed to be proportional to is the exposed surface area of the water. So if you think of the water in the tank here, or in the cone, the exposed surface area is going to be whatever you have on the surface here, and that's just a circle. And the area of a circle is just pi r squared. So what we want to do is we want to show that dV dt is equivalent to k times the area of the circle, the area of the exposed surface. So if we're looking to show this and then to find the constant of proportionality, what we're going to want to do is we're going to want to rewrite dV dt so that it probably has a pi r squared in it somehow. If we can get dV dt to look like this right side of the equation, something that involves a pi r squared, we should hopefully be able to then solve for k. Let's see, dV dt from the last screen, if I go back to part B, when we took dV dt, we didn't have r in our formula for volume, we had h, because what we had access to was this dH dt. So we used a relationship between r and h that we established with similar triangles here to go and take our volume formula to go from depending on both r and h, like it did here, to just depending on h, like it did here. This time around, what seems to make more sense is to do something similar, but we want our volume formula to depend only on r, since over here we have something that involves r and not h. So let's see, the volume formula right here, we want to substitute something in place of h so that we can go ahead and have a volume formula that depends only on r. And if I go back to that previous screen one more time, we established the relationship using similar triangles between r and h. H is equal to 2 times r, h over 2 therefore is equal to r. Well, if h is equal to 2r, I can substitute 2r in place of this h, and that'll hopefully get us to where we need to be in part C here. So my volume formula is going to be 1/3 pi r squared times, in place of h, well, again, stealing that work, h is equal to 2r. So I'm going to put 2r in place of that h. So I'm going to have 2r here. And now, before I take my derivative, I do want to simplify this a little bit. So volume dependent on just r can be rewritten as, well, let's see, I have a 1, a pi, and a 2 in the numerator. I'm just going to write that as 2 pi in the numerator of this constant. And then I just have a 3 in the denominator. So I've accounted for this, I've accounted for this, I've accounted for the 2, and then r squared times r is r cubed. So I haven't done any calculus yet, I haven't taken any derivatives, but now I can go ahead and take the derivative of this with respect to t, because I want to show that dV dt is equal to something with a pi r squared in it. So dV dt is going to be equal to, well, this is a constant, so that's going to be a part of my derivative. And then the derivative of r cubed with respect to t, well, since the radius of the water in the container is decreasing, it's getting smaller as the water evaporates, r is a function of t, so I'm going to have to use implicit differentiation here. So the derivative of something cubed is 3 something squared. I'm going to leave the inner function r there, and then I'm going to finish the chain rule by taking the derivative of r with respect to t. Let's see, do we have what we need? Well, we're getting close to what we need. And what I mean is, do we have a pi r squared anywhere in dV dt? And we definitely have a pi, and we definitely have an r squared. So let's just clean this up a little bit, and then we'll go ahead and we'll take what we have here, and we'll substitute it in place of dV dt. So dV dt in a simplified form can be rewritten as, well, I have a 3 in the denominator, and I have a 3 in the numerator, so I'm just going to get rid of those. And then what I have is I have a 2, I have a pi, I have this r squared, and then I have dr dt. If I substitute this whole entire right side of the equation in place of dv dt, I'm looking at, I'm going to change the order a bit, right? This is just all multiplication. I'm going to put the 2 and the dr dt first. So I'm going to have 2 dr dt times pi r squared equals, right? So I've put dv dt in a simplified form here. And now that's going to equal k times pi r squared. What we've basically shown is that what they asked us to show is definitely true. We've shown that dv dt, which is again right here, and that's kind of a sloppy r, it looks more like a v. Let me try to clean that up a little. We've shown that dv dt has a pi r squared in it. This is a constant, this is a constant, so yeah, there's some constant of proportionality here that makes the original claim true. If we want to figure out what that constant k is, divide both sides by pi, divide both sides by r squared, and what you get is 2 dr dt equals k, right? The pi's cancel on both sides, the r squareds cancel on both sides when you divide each side by pi r squared. So what does k equal? Well, now the only thing left as a little bit of a mystery is what dr dt is. If we steal some of the work that we did from part B one more time, I want to know what dr dt is. I have this nice little relationship between h and r right here. H is equal to 2r. I'm going to bring that relationship to this new screen. If h is equal to 2r, I can figure out what the relationship between dh dt, which they give us, and dr dt is. Taking the derivative of both sides of this with respect to t is going to give me that dh dt is equal to 2 times dr dt. What does dr dt equal? Well, if dh dt is negative 3/10, and I'm trying to solve this for dr dt, I would just divide both sides by 2, or rather than dividing by 2, since this is already a fraction, maybe multiply by the reciprocal of 2, multiply by 1/2, and that's going to give you negative 3/20 as the value of dr dt. So what does k equal? Well, if we take negative 3/20, put that in place of dr dt, we're looking at 2 times negative 3/20 as what k equals. And if we simplify this, you can divide this and this both by 2. So that's going to become a 10, that's going to become a 1. So it looks like we end up with 1 times negative 3 over 1 times 10, or negative 3/10 as the value of k, or our constant of proportionality. So it's a little bit different, a little bit tricky. Hopefully that helped you out.